Hey guys, today's lesson is about applications of logarithms, and with these applications the main goal is to work with different formulas. These formulas are given to you, so we're going to go through 4 examples. We're going to talk about what the formulas mean and how to use them properly. So the first thing we're going to talk about is Newton's law of cooling. You can see the formula here and the things we need to know about it. So the first thing that we're going to define is this T sub A. T sub A is what is called the ambient temperature, and this is whatever that surrounding temperature is. So if something is in a room, it's the temperature of the room. If we're talking about outdoors, it's the temperature of the outdoors. This is the same T sub A that you see right here in the formula as well, so we're going to use it twice in that equation. Then we have T sub 0. This is the initial temperature of the object, so whatever is cooling down, we have to know what temperature it starts at. And then the K value here, this is just some constant, and this changes based on the object. This is either going to be given to you, or like in today's example, we're going to solve for K before we can answer any other questions about the model. So let's take a look at the example I have here about a cup of coffee. So it's made with boiling water at a temperature of 100 degrees Celsius in a room with the ambient temperature of 20 degrees Celsius. We then know that after 4 minutes the coffee is cooled to 90 degrees Celsius, and it asks us what is the temperature of the coffee after 8 minutes. Okay, so asking for the temperature of the coffee is just asking us to solve this problem here. So let's go ahead and start plugging in the values that we know and see where we end up. So I know that T of T is going to be equal to that ambient temperature. In this problem we know the ambient temperature is 20 degrees Celsius, plus that initial temperature, which was the boiling water at 100 degrees Celsius, minus the ambient temperature again, so minus 20, times e to the power of negative k, which we're not given any information about that constant, times t. So what I notice right here is in order to solve for the temperature after 8 minutes, I first have to know the constant. Well, that's why they tell us what the temperature was after 4 minutes, because we can use that information to solve for k. So if the coffee is 90 degrees after 4 minutes, then that means I can plug in 90 for the T of T. So I have 90 is equal to 20 plus 80 E, right? It's 80 because it's 100 minus 20. And then I can plug in 4 for T because I know that this reached 90 degrees after 4 minutes. So that's going to give me negative 4K in the exponent. I now have an exponential equation that I can solve, and this is what we did in yesterday's lesson. So I'm going to start by getting that exponential part by itself, subtracting 20 from both sides, which gives me 70 is equal to 80 e to the negative 4k. Then I divide both sides of my equation by 80, and that's going to leave me with 7 over 8 is equal to e to the negative 4k. Now that the exponent is by itself, I can take the log of both sides. I'm going to use natural log here since I'm in a base of e, and that's going to easily cancel out. So I have natural log of 7 over 8 is equal to the natural log of e to the negative 4k. Natural log and e cancel out because we have a log and an exponent in the same base. That's one of the properties that we learned yesterday. So those cancel out to leave me with negative 4k. The natural log of 7 over 8, I'm going to hop on over to a calculator to evaluate that. So remember that Desmos has a scientific calculator. We go over to function to find the natural log, and then we're taking the natural log of 7 over 8, which we see is negative 0.1335. So let's plug that in here. We've got negative 0.1335. And then to solve for k, we divide both sides by negative 4. So when I divide that result by negative 4, I get a positive 0.03338. So 0.03338. So we know that that right there is our k value, and we can go back to our original equation to plug that in. So I now know that my function is T of T is equal to 20 plus 80e to the negative 0.03338t. Okay, at this point I can now answer the question, what is the temperature after 8 minutes, by simply plugging in 8 for T. So T of 8 is going to be equal to 20 plus 80e to the negative 0.03338 times 8. And now I can go back over to my calculator and enter this just like I see it to get an answer. So I have 20 plus 80e to the negative 0.03338 times, whoops, let's stay up here, times 8. And I get 81.25 degrees. So the temperature of the coffee after 8 minutes is going to be 81.25 degrees Celsius. Okay, the next question here is radioactive decay. So with radioactive decay, we have our function here. You'll notice that there's different variables used, but the structure of the function is the same. So a sub 0 here, this is the initial amount of whatever it is that is being observed. And then we've got that e value, and then again k is a constant. Okay, and it's a constant that's dependent upon whatever it is that you're observing that's decaying. So you'll notice in this example that that k value is given to you. Okay, the decay constant is there for you, so we don't have to do anything to solve for it. This is asking us how long will it take in years for plutonium-244 to decay to 70% of its original amount. So while we don't know a specific value for the original amount, we know that our goal is to get to 70% of that initial value. So what that means is that this f of t, this ending point, is going to be 70% of the initial amount, and that can be written as 0.7 a sub 0, right? That means 70% of the initial amount is going to equal the initial amount times e to the power of negative, and then we've got our constant here, which has 8 zeros. I already counted them out so that I knew. And this is asking how long will it take to get to this point. So we know that we're solving for t in this problem. Okay, based on how this is written, because we're finding 70% of the original amount, I can begin by dividing both sides by a sub 0, by that initial amount, and it cancels it out on both sides. Okay, so 70% of the initial amount is gives us the opportunity to cancel out that initial value there. And then I have just a simple exponential equation that I can solve using logs. Since I'm in a base of e, I'm going to take the natural log of both sides. I really tried to look for a problem that didn't have so many zeros in it, but I was having trouble finding one. The natural log and the e cancel each other out, and so I'm just left with negative 0.000. You get the idea. And then natural log of 0.7, I'm going to hop on over to a calculator to solve that. So natural log of 0.7 is going to give me negative 0.3566. Negative 0.3566. And then I'm going to divide both sides by this constant here. And again, I'm going to do that in a calculator. So divided by negative 5, 6, 7, 8. All right. So I get a very large number of 40,997,119 years. Okay, so we're going to say about 40 million. Okay, so again, we're solving using a formula that's given to us and knowing how to manipulate that formula with the values that were given. The next example has to do with compound interest, and you actually have to know two formulas for compound interest based on how often interest is compounded. So when you're dealing with a bank, you're trying to save some money or invest some money, you have to know how often interest is compounded. So there are lots of options here. Interest can be compounded annually, which means it's added into the principal amount once a year. It can be compounded semi-annually. It can be compounded quarterly, monthly, right? So this is all telling us how many times a year this interest gets compounded in. When a math problem wants to be really mean to you, then they tell you that it's compounded daily, but we're not going to do that. And then the most important one is when it's compounded continuously. So sometimes interest is just like perpetually being compounded. And if that's the case, that's where this second formula comes into play. So this one is only used for interest that is compounded continuously, okay, where the R value is the rate of the interest rate. Okay, so you can have 6% interest, you can have 2% interest, whatever that looks like. So that R value is the rate. The P value is the initial amount that you deposit into an account. Okay, so the initial amount. And of course T is time, and then the A is the ending amount. In this top formula here, where we're compounding in different ways, you'll notice that really the biggest difference is this N. And the N is the number of times that it's compounded. Okay, so if interest is compounded monthly, then we would plug in 12 for N. If it's compounded quarterly, then we would plug in 4 for N. So in this example here, we have $500 that gets deposited, pays 4% interest compounded quarterly, and it's asking how much money will you have in the account after 3 years. So this one is just plugging in the information we've been given. We know that that initial amount is $500. Okay, we've got our 1 plus. We know that the R is the rate, and so we've got 4% interest, which is plugged in as 0.04, and it's compounded quarterly. So that's being divided by 4, that N value there. And that's raised to the power of 4 times the number of years, which for this problem is 3. In order to find how much money, we're now just calculating this using a calculator. I'm going to do a little bit of this by hand to make my calculator work easier. So this is going to give me 1.01 to the power of 12. So 500 times 1.01 to the power of 12. Okay, it gives me $563.41. So after 3 years, you would have $563.41. Okay, so again, the only difference is that you would use this compounded continuously, or I'm sorry, you would use this formula here if it's compounded continuously. You'll notice that that E constant is the biggest difference, and that's what we use for those problems. The last thing I want to talk about very quickly is logistic growth. Again, I want to emphasize that the variables can often look a little different. But let's focus on some of the important things. So the number on the top here is going to be the total population of whatever your problem is. That B value there is some constant, right, for how something is spreading. And then we have an A value that's being multiplied to that E. So in this one, a formula is given to you. This is pretty common for that formula to be given to you. And the first question it's asking is, what is the total population? So we just need to understand what the formula is. Total population comes from that number on the top, so we can see that that total population is 1,000. And then it asks the question, after how many days will there be 295 cases? So we are solving this equation for 295. So I would plug in 295 for f of x, and then I would be solving for t. Okay. The first way to solve for t is to get rid of that fraction there, so I'm going to multiply both sides by the denominator. I'm going to get 295 times 1.999. I can see right now I'm about to run out of time, so I'm going to add a second video. I'm going to pause here and get another video started.